Welcome to This Explainer. Today, we're going to dive right into the fascinating world of sample size calculation and hopefully make it completely intuitive for you. Because whether you're running a massive clinical trial or just putting together a local customer satisfaction survey, getting your sample size right is, without a doubt, the single most important step in your entire research design. Whenever you start a survey, an interview study, or a clinical trial, you're immediately hit with one seriously intimidating, fundamental question about your participants. How many is enough? It sounds like such a simple question, right? But it has a surprisingly complex answer. Professor Oluwadiyar really hit the nail on the head in his research modules when he noted that finding this sweet spot is one of the most ticklish problems in research. In statistics, your sample is basically just a percentage of the total population, and your ultimate goal is to use that small group to make highly accurate inferences about the whole. But hitting that perfect number, it's a massive balancing act. So here is our roadmap for this explainer. First, the Goldilocks dilemma. Second, the soup taste test. Third, variables driving sample size. Fourth, reaching data saturation. And finally, modern calculation tools. Let's jump right into part one, the Goldilocks dilemma. So if your sample size is too small, your data is literally useless. You just won't have enough statistical power to detect any real differences, meaning the study fails. But on the flip side, if your sample is way too large, you're throwing away money and wasting time. For example, let's say you're running a clinical trial for a new treatment targeting osteoarthritis of the knee. You know, that degenerative joint disease where the protective cartilage gradually wears away, leading to severe pain, stiffness, and difficulty moving. If you test more people than mathematically required for that osteoarthritis treatment, just to pad your numbers, that is a massive waste of clinical resources and totally crosses ethical lines. You have to optimize. Okay, moving on to part two, the soup taste test. To really visualize this, think of sampling a population like taste testing a giant boiling pot of soup to see if it needs a bit more salt. The entire goal of a sample is to figure out the truth of the whole based on just a tiny little fraction. And what's really amazing here is the sheer efficiency this represents. Think about it. You absolutely do not need to drink the entire pot of soup, which represents your whole population, just to know what it tastes like. A few well-chosen spoonfuls, your sample, give you all the information you need to make a perfectly accurate judgment. But here is the catch, and it's a big one. Those spoonfuls only represent the whole pot if you literally stir the soup thoroughly first. If all the salt has sunk down to the bottom and you just take a quick scoop from the top, well, your spoonful is lying to you. That stirring process, that is exactly how random sampling works in research. You have to mix up your population so that every single demographic has an equal chance of ending up in your spoon. Which brings us to part three, variables driving sample size. Let's talk about the margin of error, which basically reveals the level of imprecision hiding in your data. Imagine taking a really tiny sample, say just 50 respondents for a survey. With that size, your margin of error is a massive 14%. That means if 50% of your sample says they like a product, the real number in the general population could be anywhere from 36 to 64%. That is highly, highly imprecise. However, if you bump that sample up to 1,000 randomly selected respondents, something magical happens. That margin of error drops dramatically to a very reliable 3%. Suddenly, you have a much tighter, vastly more accurate view of reality. But this also brilliantly illustrates the concept of diminishing returns. You might be sitting there thinking, well, hey, let's just survey 2,000 people to be incredibly safe. But actually, doubling your sample size from 1,000 all the way to 2,000 only buys you a tiny 1% improvement in your margin of error, dropping it from 3% down to 2%. The massive cost of acquiring 1,000 more participants almost never justifies that tiny bump in accuracy. So beyond just the margin of error, determining your sample size relies on a delicate balancing act of quite a few variables. Take population homogeneity, for instance. If you're studying a very uniform, similar population, your data is already tightly clustered together, meaning you can easily get away with a smaller sample. The expected effect size is a huge factor, too. I mean, detecting massive, obvious differences between two groups is easy and requires a small sample, but detecting a tiny, subtle difference, that requires a massive sample. And of course, if you're using complex analytical techniques like multiple regression, you automatically need more participants just to feed those hungry algorithms. Now, all of those variables ultimately get plugged into mathematical formulas that look a bit like this one. But don't let the math scare you.
This is simply how we ensure we find that exact, scientifically sound number for quantitative research. It takes your z-scores for significance and power, multiplies them by your standard deviation, and then divides by your expected difference to spit out the absolute optimal sample size. It's basically mathematical magic that prevents both failed studies and wasted resources.
All right, part 4, reaching data saturation. So what if you're not doing a math-heavy study? What if you're conducting in-depth theory-based interviews rather than running massive numerical surveys? Well, you obviously can't rely on z-scores and standard deviations for that. Qualitative research is all about depth, narrative, and beliefs, not statistical generalization. Instead, qualitative researchers rely on a really fascinating concept called data saturation. Saturation is basically the exact moment when conducting more interviews stops providing any new shared beliefs or information. It's that point where you realize you're just hearing the exact same things over and over again. Let's look at this graph from a real study that was mapping out the beliefs of medical practitioners. Notice how that thick black line shoots up really sharply at first? That is the researchers discovering lots of brand new beliefs with every new person they talk to. But look closely at what happens right around participant number 10. The line just dramatically flattens out. It totally plateaus. That flattening is data saturation visually represented, proving that pushing forward to a 15th or 20th interview would literally just be a waste of everyone's time. To operationalize this and actually make it an objective rule, researchers often use what's called the 10+3 criterion. Here's how it works. You conduct an initial analysis of 10 interviews. Then you keep interviewing, but you stop exactly when 3 subsequent consecutive interviews fail to add any new shared concepts to your list. It's such a brilliant, highly structured way to know exactly when your spoonfuls have given you the full flavor of the qualitative soup. And finally, part 5, modern calculation tools. Now, for those of you working in quantitative fields who saw that formula earlier and instantly broke into a cold sweat, you can totally relax. You just don't have to crunch those massive statistical formulas by hand anymore. Manual calculation is ridiculously slow and carries a super high risk of error. Today, researchers use software tools like GPower. These apps instantly calculate your ideal sample size with a much lower risk of error. Literally, all you have to do is plug in the basic parameters, like a 5% significance level, an 80% statistical power, and your expected effect size, and the software instantly tells you, hey, you need exactly 36 participants per group to have a valid clinical trial. It's that easy. And looking forward, technology is poised to make this even easier for us. Integrating artificial intelligence and machine learning into sample size determination is soon going to offer predictive models that can optimize your sample sizes completely on the fly. They'll be able to dynamically adjust based on real-time data trends. This is absolutely going to be a game changer, especially for resource-constrained researchers all over the globe who need highly efficient, cost-effective study designs. So as you prepare to stir the pot for your next big study, whether it's a massive survey, a clinical trial for joint health, or in-depth qualitative interviews, how will you ensure your spoonful is perfectly engineered to reveal the truth? Because remember, the validity of absolutely everything you discover depends on hitting that Goldilocks zone of balancing accuracy, ethics, and resources. Thanks so much for joining me for this explainer today, and I really hope this helps you find your just right number.